Yes, I'm ready. Yes, I'm ready. Yeah. Yes, yes, you are correct. Yeah. Okay. Assalamu alaikum and good morning. Can you all hear me? Okay. Can you hear me?
Yes, Prof.
Yes, Prof.
All right.
Yes, Prof.
Dr. Zahirani? Okay. All right. Thank you very much once again. Let me thank the organizer of this webinar, Dr. Noura Sikin, for inviting me to give this seminar and share our experience. And I also would like to thank Dr. Zahirini for making this arrangement and for hosting this today. Let me try to share my slides now. I always mess up things on Google Meet. I don't know why. I hope it will go okay today. Okay. So I just shared my document. Please let me know if you can see this.
Yes, Prof.
Okay.
Yes, Prof.
Shall I start? Okay. So let me thank the audience also. And also I see some known faces from Thank you all very much for making your time. So what I would like to do, how many minutes do I have? Dr. Zahir? Okay. I think, yeah. I think that should be fine. Yeah. But you stop me if I overrun the time. So the title is this, Nanostructured Semiconducting Metal Oxides for Highly Sensitive Gas Sensors. I divided the lecture into these a few topics. So after a general introduction, I will talk about semiconducting metal oxide gas sensors in generals, and then I will share our experience on working with two particular groups of semiconducting materials. So one is titanium oxide, aluminum oxide, which is a mixed oxide. Other one is zinc oxide, tin oxide based nanostructures. The reason we have been working on these two material is this. So our aim is to produce these nanostructures at a low cost. So we are researching into quite simple way of producing these nanostructures. And we use mixed oxides because we see that there are evidence in the literature that when you combine different oxides, synergy can happen, and that can improve the performance of these oxides as gas sensors. And obviously, we will work on one-dimensional nanostructures, which again has a lot of advantages, and we will talk about it. And finally, we will conclude this session. Now, let me take you back to 19th century or early 20th century. This is a typical coal mine. And probably you know that in coal mine, accidents happen. Carbon dioxide, carbon monoxide, methane, if they are present in dangerous amount, people get killed. And at that time, they used a sensor to sense these dangerous gases. And that sensor was this. So this is a bird called canary in English. It's a bird that loves singing. So what the miners would do, they would bring these birds with them in the underground shaft of the mine. And normally this bird would keep on singing. And if there is a dangerous level of gases, they could detect it early, they would stop singing and ultimately die because of excessive amount of these gases. And when the miners see that the birds are dying, so they get the danger signal and they would evacuate as quickly as they could. Nowadays, of course, we don't use such natural sensors. So we have developed a lot of technology to produce sensors that can detect gases. And the detection of gas is really very, very important in all sorts of industry, starting from automotive, safety and security, mining, I just mentioned, oil and gas, manufacturing, etc., etc. And if you look at the application at the bottom, which is in medicine, there is a new area where analysis of breath can give a lot of information about the disease that a patient may be suffering. And gas sensors can bring a lot of new innovation in this area. And by using this breath, one can, in principle, detect a lot of dangerous diseases like cancer, like diabetes, etc., etc. And there is a big emphasis on research going on to materialize this technology. The medical professionals and the engineers and scientists are working together. I will not share anything on this topic today. I just want to introduce you because we have started working on this. and hopefully in a few months or years' time, we can have enough data. And I see some of my colleagues collaborating on this project is also attending this lecture. So gas sensor market enjoys quite handsome growth and some cumulative aggregate growth rate of about 7.5%. So it's an area which is critical in many sectors of the economy. And the technology driver in the gas sensors are, number one, we would like to have smaller sensors. And you know, in this era of IoT and this artificial intelligence, we envisage that sensors will be everywhere. And gas sensor will be one important component here. And these sensors should be compatible with this wireless communication and IoT. They should have less power so that they can be independently run without trouble. They should be reliable, etc., etc. So a technology that we want to use for gas sensors should meet some of these requirements if they want to compete in the future. And there are some key market players which are mainly from the US, Japan, and Europe. There are a few companies who are growing now in South Korea, for instance, and also in China. And some of them have sales offices or department in Malaysia. But mostly the companies in Malaysia that deal with these gas sensors, they sell their the product, those are manufactured outside. And we don't have a very active research base on gas sensors in this country, which is often an impediment to researcher because we cannot collaborate with appropriate companies in order to materialize our ideas into some useful technology. Gas sensors can be of different types. They can work on the principles of electrochemical information. They are also types which is called solid state gas sensors, and that is the topic of our discussion today. These are based on metal oxide semiconductor. We have photoionization based devices. We have catalytic sensors for gases. Infrared gas sensors are also common. And besides this, there are a host of different types of scientific principles which are being pursued to detect gases in different situations. For us, we will concentrate today on these metal oxide gas sensors. So what I will try to give you now an overview of these metal oxide gas sensors in general before we share our experience. Metal oxide based gas sensors have a lot of advantages. They have high sensitivity. They can respond quickly compared with other sensors to different gases. They can detect quite a large number of gases. They are non-toxic in nature. They can be produced at a lower cost with easy fabrication process. They can be made really small in size. And above everything, these type of gas sensors work on the principle of what we call chemi-resistive, which means that they change their electrical properties when a gas interacts with them. And as a result, since it deals with electrical quantities, so they can be easily integrated into electronics and miniaturized. However, they are not free from disadvantages. They have lower selectivity. So if you have a mixture of gases, many of those semiconductor-based gas sensors find it difficult to selectively target a particular gas. They also need to operate at higher working temperature in order to have adequate sensitivity. The working principle, as I mentioned already, is chemi-resistive in nature. That means that when you expose the sensing material, the active material, to a certain gas, then redox reaction happens on the surface of that material. So oxidation reduction happens. And as a result, charge carriers are transferred and generated. And because of that, the resistance changes. And we measure the resistance as a function of the concentration of the gas. And from there, we can find out the gas or detect the gas and their concentration in a particular system. Normally, as I mentioned, that we use a slightly elevated temperature to do the detection in an effective and efficient way. And also these gas sensors are produced in a way which expose larger surface area because all the reactions happen on the surface. In terms of band structure, the principle is quite simple. So if I start with an N-type metal oxides, so in the vacuum, so you have your conduction band, which is close to the Fermi level, and then you have the valence band below. Now, we do not operate in vacuum. We are immersed in air. So the air contains one of the active gases, which is oxygen. When such N-type semiconductor is exposed to oxygen, then oxygen adsorbs on the surface. And in that adsorption process, the oxygen takes up the electron from the surface to produce different species, which is shown here. And as a result, a depletion zone is created at the surface, an electron depletion zone. And because of the presence of this electron depletion zone in air, so the conductivity or the resistance decreases, or the conductivity of the N-type semiconductor increases when it is exposed to air. Now, if in the air we have a gas that we want to detect, and let's say this gas is a reducing gas, then the reducing gas will interact with the semiconducting surface. And the reducing gas will donate electron to the surface of these N-type metal oxides. And as a result, the depletion zone will decrease in its width, and the resistance of this material will decrease. And if we measure the resistance in a particular gas, then we have two quantities now. One is Ra, which is the resistance in air, and one is Rg, which is the resistance in a particular target gas. And Ra is obviously greater than Rg. And we now define the response of this material to the gas by using this ratio Ra over Rg. Now, this is greater than 1, as you can see, and it depends on the concentration of the reducing gas that is in contact with the N-type semiconductor. So if the gas concentration is high, then we have a higher value of this quantity. Now, we have situation that I will explain a little bit later. Now, let's look at this depletion layer thickness. This is typically on the order of 100 nanometer. And we will keep this in mind because we will see why this is important. Now, the gas sensing response can be defined depending on the type of oxide and type of gases that we use. It could either be Ra or Rg, because the change in the resistance will change sign depending on the material and the gas. There are quite a number of characteristics that need to be satisfied for a commercial gas sensor. I didn't list down all of them. I just note a few of them, which probably we will discuss, particularly the response. I think I will discuss more on the response today. Then we have sensitivity, selectivity, and responding speed etc. Although the principle, as you have realized, is rather simple to understand, but the actual science that is underpinning gas sensing characteristics is quite complicated. And we don't have any model, in fact, any theoretical basis to design a material to characterize these gases. We still have to do a lot of experimentation, trial and error, and experiment guided by scientific principles and data that is published, etc. So that is still the basis of new development. And I just list down a few of the characteristics that determine the gas sensing properties of these semiconducting oxides, like surface area, porosity, agglomeration, the donor density, the defect type and defect density, stoichiometry, acid-base property, nature of catalyzing catalyst effect of the material towards a particular gas, sensing temperature, etc. I come to one of the main themes of this work. As you realized, we mentioned that these are nanostructures that we will be dealing with. And why this nanostructure is important, we know in general that nanostructures can give rise to interesting properties. For this particular application of gas sensing, let me explain why it is so vital. Now, we know that we use material in polycrystalline state in the case of this semiconducting gas oxides. And when we use this material, the gas absorption happens only on the surface in a very thin layer. And the rest of the material, gray ones, remain inactive or passive. Since a very tiny fraction of the material is active in gas sensing, that means that the signal that we get is not so strong. Now, you probably remember that this length of the initial depletion layer is about 100 nanometer. Now, when we reduce the grain size of the material, as the material grain size reaches the magnitude of this 100 nanometer or even less, then what we see is this, the whole material itself now take part in this charge transfer events. And the material as a whole in small dimension, when they are produced in small dimension, becomes active, and that gives rise to large signal, and that improves the performance of the device, of the sensor. And that is why the trend now is to research into the nanocrystalline material or nanostructured material in order to improve the gas sensing performance. And some of the important benefit that we get out of these small crystals or small nanostructured material is that number one, as I mentioned, the sensitivity increases because we get large signal as most of the material or larger fraction of the materials become active in the reaction. We can reduce the device dimension, which is very important now in technology. Miniaturization is the trend. And power consumption also is reduced. And this is also another very, very important characteristics that we want to have. Just to give you some idea what we mean by these reducing the dimension. In early years, a few decades ago, the gas sensors were used in thick film form, where we have tens of micrometers of oxide used as the gas sensing elements. Then the trend was towards using a thin film, where we have a few hundred nanometer thickness. And now the trend is towards producing the nanostructures, which are much finer in size, just a few tens of nanometers. For instance, we have now these nanowires of few tens of nanometers. And as a result of this, we have many benefits. So one benefit that we have seen is that this dimension is smaller than the dimension of the typical depletion layer. So we have the whole material is active. Number two, in this particular form, you see a lot of porosity. So the gases can diffuse and the whole material system now become active. And researchers around the world are now investigating this, particularly this 1D oxide or one-dimensional metal oxides, and all sorts of oxides are being investigated. So zinc oxide, tin oxides are very important material, titanium oxide. We also have indium oxide, tungsten oxide, and so on. Now, let me go into the next phase of our talk today, and that phase is about our own experience. And I'll talk about this titanium oxide, aluminum oxide system, and I will present it in 4 subsections. So first I will discuss the synthesis, because we had to develop a process how to make them, and obviously, the process that we intended to have is a low-cost, low-tech process. And after the synthesis, we characterized what we produced, and then we fabricate sensors out of this, and then gas sensing properties. Let me concentrate on this one first, the synthesis of these oxides. There are a lot of techniques that researchers have been trying to produce 1D nanostructures. These are wet processing, solid state processing, molten stage, and so on, vapor phase, etc., etc. And we have selected a process of solid state processing. And this is a very low tech. We just use a metal and then we oxidize them in a furnace. And of course, we have to optimize the condition, otherwise we don't get nanostructure, we just get thick scales or thick films of oxides. And this is how we do it. We have a furnace where we control the temperature, we control the environment in a quartz tube, and we keep the sample inside. And by controlling the gas and other conditions, then we find a window of processing where we can grow nanostructures or one-dimensional nanostructures in an efficient way. And I will explain to you how we optimize them. So we started with this particle. And maybe I have to give some brief introduction to this particular type of particle, which is called Ti64. It's a commercial alloy of titanium, which is very easily available. It contains 6% aluminum and 4% vanadium. And the reason why we started this with this alloy is that we could also produce oxide on pure titanium. But looking at the literature and based on our own experience, we found that producing good nanowire on pure titanium by this oxidation method is difficult, and is the window of the parameters that we need to achieve is very narrow. Then we thought that this alloy, which is very widely available, let us try this. And our motivation was that in addition, that this alloy contains alloying element, particularly aluminum. And we have seen in the literature that when aluminum oxide is mixed with titanium oxide, the gas sensing property can be influenced. And this motivation was the basis for choosing this titanium oxide, this Ti64 alloy for our particular use. And once we have this commercial particles of this Ti64, we looked at the effect of oxidation temperature, gas flow rate, oxygen concentration, effect of residual stress, because we also know that in order to grow a good nanowire, the residual stress inside can play a critical role. So we wanted to play with that as well. This is the effect of temperature. We grew the nanowire in a controlled environment where we have argon gas mixed with tiny amount of oxygen, because we cannot do the oxidation in air. If you do that, then you create thick layers of oxide. We don't get the nanowires. Now, by looking at this pictures, you see that from 650 to 900, at high temperature, we don't get nanowires. These thick bundles of oxides that form here. And we get nanowires in a narrow range. For instance, we see a few of them here at 750, a few at 800, and so on. Quite very few in 700 also. So our temperature window, as we determine here, will be about 700 to 800. And we will show later on that probably 750 is the best temperature that we could use. This shows the combined effect of gas flow rate and oxygen concentration. I just remind you, we use a carrier gas, which is argon, and then we add a little bit of oxygen, because these nanowires grow in oxygen-deprived environment. And we varied the concentration of oxygen from 5 ppm to 105 ppm. And the flow rate was varied from 20 standard cubic centimeter per minute to 500 SCCM. And as you can see that there is, again, a narrow window where we can get some nanowires. And that window is about 500 SCCM, 15 ppm, 40 ppm. So this is the range. In fact, when we document all this in a systematic way, so we prepare a map of where we get the nanowire, and we plot in one axis the partial pressure, the dynamic partial pressure of oxygen and the oxygen concentration in the tube. And we see a box within this. In our experimental condition, we find that the nanowires grow only within this box. We have carried out tests, and the test conditions are all in the purple dots. And we find that the purple dots, which are within this box, give us good enough nanowires for our sensing application. Then we wanted to see the effect of residual stress, and we imposed the residual stress by ball milling. So we subjected the incoming material, the Ti64 particle that we saw, we subjected them to ball milling for different time period. So if the time is longer, then we induce more stress. And these are the, I think I skipped the particle size distribution. What I want to show is this one. So as a result of ball milling, we induce stress, as we all know, and we wanted to calculate the stress, the residual stress inside. And we use this d sine square chi method from X-ray diffraction, and we analyzed the 103 plane, the intensity of the 103 plane of this titanium particle. And what we see here is this. So in the original titanium oxide, without milling, we see that there is a residual stress, but that is mainly tensile in nature. And when we do the ball milling, we actually change this residual stress, and we impose quite a large amount of compressive residual stress inside. And we know from the literature that compressive residual stress can help grow the nanowire. So we wanted to have this, and that is why. So we would use this ball milled particle to grow our nanowires. And this is a demonstration how stress is so effective. So as you see here, so this is 0-hour ball milling, which means that the ball milling was not done at all. And then we increased the ball milling time from 20 to 30, from 2 to 30 hours. And we see that at higher, longer ball milling hours, we grow quite nice, impressive nanowires on each of those particles. And we tended to use this condition, so 20-hour milling, because if you go longer than this, it actually you increase the power consumption. So that, in our experience, gave good enough coverage and amount of nanowires. The temperature also played a very important role. If you increase the temperature like 800 degrees, you see that you don't grow the nanowire. So we stuck to this condition as 750, where we get a decent quantity of nanowires on particle that was milled for 20 hours. We did the X-ray diffraction on the nanowires after we prepared them. And what we see is that the nanowires consist of two phases. One is rutile of titanium oxide and the corundum of aluminum oxide. And you remember we started with the particle which was Ti64. It contained titanium and 6% aluminum and 4% vanadium. And we have seen that the vanadium did not take part at all in this nanowire formation. So we only have titanium and aluminum that is in the nanowire. But we don't know from this XRD in what form, in what way they are mixed, in what morphology. In addition to the stoichiometric rutile, we also get some sub-stoichiometric oxides as well, in small amount though. XPS was used to confirm the nature, the chemical nature of those oxides. And indeed, we have found out that we have this titanium oxide and also aluminum oxide from the binding energy calculation. We have done the transmission electron microscopy. And if you look at one single nanowire, you see that now we have an idea about the morphology. It looks like that it has an inner core and an outer shell. And when you zoom in at the outer shell, when you do the high resolution transmission electron microscopy, you actually see the fringes of the lattice, and this corresponds to 111 fringe of aluminum oxide of the shell. We carry out in STM mode the analysis in a very accurate spatial resolution. And what we see here is that along this nanowire, the aluminum concentration is high at the edge and it's low at the middle, the green one. So that tells us that the nanowire that we have is possibly the core that contains titanium, on the other hand, is high at the middle. So it's probably titanium oxide at the middle and aluminum oxide at the outer surface. And indeed, when we do the electron diffraction, this is confirmed. And what you see here, the electron diffraction pattern, so all those spots belong to the titanium oxide, and the streaks that we see here, that they belong to aluminum oxide, and they appear as streaks because of the very small dimension in a direction perpendicular to the electron beam. And we also notice that the aluminum oxides are very small crystals in size. And we determine the growth direction as well, so which is 002 direction for rutile. So this is the growth direction, which is 002 in this particular case. And this is same or more or less similar for other nanowires as well. And I may not be able to explain all this, but let me just tell you what happens. So everything happens at the surface. And the process of this nanowire formation is a little bit complex. So when you do the oxidation, segregation of things happen at the surface. And we see that aluminum, the blue one, so aluminum tends to segregate at the surface, and it creates a complex layers, in fact. So an inner scale that contains titanium and the outer scale that contains aluminum and titanium mixture. And on that surface, the nanowires grow. So nanowires grow on this particular surface. And before the nanowires grow, a lot of other things also happen. And I will just summarize our finding that we have seen. So what we have found out that if you have a large enough particle, then at the core of the particle, we have unoxidized titanium alloy. And then at the outer surface, we have inner scale of titanium oxide, which is mainly pure titanium oxide. And then an outer scale, which is a mixture of titanium oxide and aluminum oxide. And on top of this, now we have this nanowire formation under strict conditions. Obviously, when the particle size is small, then the whole oxide particle is oxidized. And we proposed a mechanism how this grows. In fact, it was not our discovery. We find in the literature people explaining things in different systems. And from there, we borrowed some idea. And here we propose that what happened here is a stress-assisted one-dimensional growth. And initially, aluminum tend to segregate to the surface. And we know this from the high temperature corrosion literature. People have found that out earlier, that aluminum tend to segregate there. And once aluminum segregates to the surface, it forms oxides at different places. And titanium then also tend to diffuse along the grain boundaries, and then they move up. And when they are moving up and are exposed to oxygen, they also become oxidized. So we now have at the outer layer a mixture of oxides of titanium and oxides of aluminum. And you probably remember now that we have a material which is highly stressed, a large amount of compressive stress is inside. So if you heat them to high temperature, the atoms will tend to diffuse in order to reduce this compressive stress. So that is the driving force. So that will push the titanium atoms towards the surface, and aluminum will now provide what we call a confinement. So aluminum oxide will provide a confinement, and then titanium will grow inside this. So this is a mechanism that happens. So once we have optimized our titanium oxide nanostructures, our next step is to prepare the sensors. And the sensor preparation is straightforward. So we use a platform which is interdigitated electrode made from gold, because we use a high temperature, and this is deposited on alumina substrate. And we prepare an ink based on the oxide that we have exposed to the oxygen under a strict condition, and the particle contains those nanowires on the surface. So we mix them in a liquid to produce an ink, and then we dispense the ink onto this interdigitated electrode. And we need to carry out some optimization, because we varied the amount of solid nano structures in the ink, and we varied it from 1 to about 20%. And what we see that when the loading of the particle in the ink is very small, then the particle do not breach them. So we have high resistance and they cannot work as the sensors. On the other hand, if we have large amount of particle loading, then we create a very thick layer. And this is also not good for sensing, because they actually short the whole thing and we don't get the change in resistance as a function of gas. So we have, again, one condition where we optimize them and they just touch each other. And in doing so, they do not short the whole system. And this is the mechanism that we propose here that is happening at low concentration of particle. what we have is that the gaps in between the particles remain, so we don't have a continuous conduction path, and as a result, the resistance is very high. And on the other hand, if we have very thick layers, the layers beneath the top surface, they actually get reduced in reducing environment, and they become metal and they become active now. And they just short this whole thing. So this is also not good. And this is the condition, ideal condition that we want to have, where the particle just touches each other at the nanowires, and the conduction happens through the nanowires, because these are the active material that we want to have for our gas sensing. And this is the result of the resistance measurement on this nanowire in ambient. And as you can see, that when the particle loading is less than 20%, we have very large, less than 1 wet percent, sorry, then we have very large resistance, and we cannot measure anything. On the other hand, if the particle loading is very high, the resistance is very low, and they are not sensitive to gases. So this is the range about, let's say, 2 to 5% of loading, where we can optimize the sensor, and the sensor performs satisfactorily. So we use this, and then we prepared our sensors. And once we prepared the sensor, we put it inside a tube furnace where we can control the temperature. We also control the gas flow by accurate mass flow controller. And we can go down to about 20 ppm in our system now. And we record the data during this whole process, where we introduce different gases, and we see the variation of resistance as a function of time. And this is the actual setup. So this is the furnace, and these are the gas flow system, etc., etc. Okay. Now let me show you the initial result. So we basically measure the resistance, and we introduce gases, and we measure the resistance as a function of time. We divide it into 3 zones. Zone A is the zone where we have the carrier gas, and for this measurement we use nitrogen as the carrier gas, which is not active gas and widely available in the atmosphere. And when we do measure the resistance, so we get a particular value for this material, then we introduce different gases, and that is represented in zone B. And we use a wide variety of gases, in fact. So hydrogen, hydrogen sulfide, carbon dioxide, carbon monoxide, etc., etc. And out of those gases, you notice that there are 2 oxidizing gases, nitrogen dioxide and oxygen, and the rest are reducing gases. And the response is also consistent with the theory that we described. So with reducing gases, the resistance decreases, as you can see. With the oxidizing gases, the resistance increases. And from there, we calculate the response. And as we see that the response of the sensor TiO2 aluminum oxide mixture depends on the gas. For some gases, the response is very low. And the response is quite substantial only for 3 gases here. So one is hydrogen sulfide, another one is methyl alcohol, another one is ethyl alcohol. So these are the 3 gases which respond very well towards these gas sensors. We can also look at the sensors at different concentration and different time, and we see that even at 20 ppm concentration, we can get some decent signal, which can be useful for detecting these gases. And the response of the gas, of the sensor towards different gases changes with gas concentration. Initially, the response changes quite rapidly, and then it levels off, which is a normal, usually a normal behavior that we see in other cases as well. So to summarize what we see, if you plot the response, we see that the gas sensor that we have designed has got sensitivity towards methyl alcohol, ethyl alcohol, and hydrogen sulfide. And the rest, the response is quite low, which means that this particular sensor can be targeted for measuring these gases in the presence of other gases, because those other gases will not interfere appreciably with the measurement. And here is the description of the mechanism. I probably will not go into deep because my time is running quite fast, as I can see. So I just want to highlight one particular thing. You probably have in your mind why aluminum oxide, because we know this, the aluminum oxide has got a band gap of more than 8. So this is a true insulator. Whereas we need semiconductor 3 plus, the band gap should be 3 plus electron volt. And when we mix them together, what we see is that aluminum oxide is forming a layer, continuous layer at the top surface. And we were initially puzzled why this insulator, in spite of this insulator, we still get the signal from this. So we looked into the literature and we found out that there is a mechanism that has been suggested already by Fowler and Nordheim. They have shown that when aluminum oxide is present on a conductor at a very small thickness, lower than 40 nanometer, then actually this layer can allow electron tunneling. And we believe the same mechanism is happening here. So in spite of the presence of aluminum oxide, which is obviously good for us because it helped to create those nanowires. So that is good for processing perspective. But at the same time, it is also not interfering with the gas sensing measurement. So it is not behaving as an insulator. Otherwise, we would not get any signal. It is behaving in a way that it allows tunneling, electron tunneling, and then gives us the signal that we need. And after we have done this analysis of gas sensing, we also need to look at what happens to the gas sensor after this measurement. Are they stable? Can we do it repeatedly? Because in commercial practice, we have to do that. So what we did is, after the gas sensing, then we allow them, cool down, and then we do additional analysis on those used gas sensing material. And when we do the Raman spectra, we particularly notice one thing. So in the case of the material which was exposed to alcohols, we see a deposit of amorphous carbon, which is not present in the original material, which is not present in the material exposed to hydrogen sulfide. So that signals to us that things are happening there. And of course, what we suggest now based on this, we remember that in the presence of this alcohol, the sensitivity is really very high. So we propose this is what is happening. So when we expose our material to this environment containing alcohols, then as a result of interaction with this, we have a deposit of this amorphous carbon. As a result, the resistance decreases tremendously and we get a very high response, and which we cannot get in other material like, let's say, other gases like hydrogen sulfide, because the mechanism is different. Now, this leads us to dig a little bit in detail into the literature, particularly our colleagues in the catalysis. They have done a lot of work in the past on the interaction of these chemicals with oxides from, of course, they did it from catalyst's point of view. And what we find in those literature is that when we expose at high temperature our oxides to those gases, then they are dissociated with the methoxide and ethoxides. And it's interesting that what we see here is that as a result of those interaction, a series of reactions can happen. So the ethoxide formation can happen. We have ultimately, after that, deposition of this amorphous carbon from these ethoxides. that we have seen, and then some other reactions involving hydroxyls also happen if it is present there. And after that, what we do is we looked at the structure once again under ASEAN. So we are afraid that the nanostructure could be quite fragile, quite sensitive, and they may not be stable enough. But what we see is, to our great satisfaction, that after a large number of cycles, and even we stored it for 6 months and years, in fact, in the storage in the lab, and then when we examine this, that the nanostructure are still there and preserved in a nice way. So that shows the stability of the structure that we produced. All right, now I have another one, so I have to take the permission from my host.
Yes, bro.
Overrun, if you do not allow, it's okay. I think I gave the main message. I can go to the conclusion.
I think it's okay to proceed.
It's okay to proceed.
Okay to proceed.
So in that case, I will quickly do it as quickly as I can. All right. So this is another oxide system which is having a great potential. So this is a zinc oxide, tin oxide based nanostructures. And again, I emphasize this, that our main, one of the main motivation is that we want to use a very simple process to produce nanostructures so that the process can be upscaled to produce nanostructure in large amount at a low cost. So we used a technique for this that I will describe in a while. So this is the main section that I will cover under this material. So one is the synthesis and characterization, and I will selectively use some of the gas sensing properties, not all. So what we did here is rather straightforward. We collect commercial zinc oxide powder, tin oxide powder. We mix them with, again, commercial activated carbon, ball mill them to mix them together, and then we heat them. So this is the so-called carbothermal reduction process. Carbon reduces the zinc oxide and tin oxide in this process. And then after this reduction, we have a vapor. The vapor then condenses, and in the condensed form, they again reoxidize, and we have now different types of structure. So this is a very interesting system. We can have many different types of nanostructures formed. So we have formed a nanostructure by vapor solid process, and then we could grow nanostructures by vapor liquid solid process also, depending on the place where we grow them inside the chamber. Let me show you the setup, which is again very simple. It's a simple tube furnace. Inside the tube furnace, we put a boat, and in the boat, we add our mixture of oxides and the carbon. We also put our alumina substrate at a distance from this, about 9 centimeter, and then we flow argon during the whole process. And what we saw is this. So once we have completed this deposition, we see that something is growing there in the boat. So initially the student ignored, and because we are interested in this. So what deposits on this surface? So that is of our primary importance. But then by looking at this, so we become curious, and then we wanted to look into this into detail. And then we found out that this is also a nanostructure. The things that grow here are also nanostructure, but they are two different types. And just to highlight you once again the mechanism to tell you, so we started with oxides of zinc and tin combined with carbon, and when we heat them at high temperature, 900 degrees, we know that this reaction will happen spontaneously, and zinc vapor will form. Zinc has a very low vapor pressure, and it will also take up some of the tin as vapor, and then it will shift. And in this process, so we did not make our system gas sealed, oxygen leaked. So the oxygen is there in a small amount, and this whole vapor of metal then gets oxidized, comes to the surface and then gets oxidized, and then we have the growth of this oxide in the form of a nanowire. And they also form on the surface of this boat as well. So they condense on the surface of the boat and forms nanowire. And I will show you some interesting morphology of the nanowires that grow at these two places. So first, let us look at the nanowire that grows on the boat. So these are the pictures. And if you look at the variation of the nanowires that form, or nanostructure rather, that forms, it changes with time. So at the beginning, there's a very thin and smooth. They are round, they are rectangular in shape. And as time grows, they become more rough in this low magnification. But if you look at high magnification, things become very clear. So what you have in the initial 15 minutes, the material that grows on the boat wall is rectangular. And we will show it later on that this is actually tin oxide that grows. And then, sorry, it's zinc oxide. I'll show you later on. And then something happened there, something depositing on top of this, and that is becoming rough, and then it takes a shape. So what we call this hierarchical shape. So we have branches coming out of it at more or less 90 degrees from this main stem. And when we do the XRD, we see that we still have two distinct oxides. In this particular case, zinc oxide and tin oxide. So they are distinct. But again, we don't know how they are mixed. So we carry out a lot of morphological tests. And at the beginning, what we see is that the initial oxide is tin oxide. At 15, we see a high amount of tin, very low amount of zinc. So the first, at the boat, tin oxide grows. And then with time, at 30 minutes, when it becomes rough at the surface, we see that additional material is depositing, and the rough thing are zinc oxide, actually, as you can see, the higher signal of zinc on the surface. And as you, and we get a co-shell structure at 30 minutes, so zinc oxide and tin oxide. And then when we keep on running the experiment at 120 minutes, so we see that the branches are forming. You probably remember the side branches, and we look at one of the side branches and we see that the side branches are basically zinc oxide. So the stem, which is tin oxide, is surrounded by a layer of zinc oxide, and then the branches are coming out. So quite interesting. Then we look at another place. So the material that forms on our place of interest, and which is the interdigitated platform for our sensors. When you look at the material that forms here, that is a big story, but I will cut it short. I just want to highlight you to this. So we see that well-grown nanowires are forming, and there is a small tip on each of those nanowires. And when we do further study, obviously we realize that the tip of this is gold. You remember that we use gold interdigitated substrate. So the gold layer was already there, and that is taking part in this. And we know that a mechanism that gold can catalyze this nanowire growth. Okay, so this layer that we get is the nanowire that we get has a 311 plane, which is parallel to the growth of this direction. And then we have a lattice parameter which matches a mixed oxide, and I'll show you the mixed oxide now. And I already wrote it down. So it's not a separate mixture of tin oxide and zinc oxide. It's actually a ternary oxide which contains zinc and tin. And we confirm this again on STM. We see the uniform mixture of tin and zinc without any shell formation. So on this substrate, we get a mixture of is tin oxide and zinc oxide, which is further confirmed here in mapping. And this is the mechanism that we find in the literature, that indeed gold can catalyze this formation, and this is called vapor solid liquid mechanism, where the tin vapor will dissolve in gold, and gold is formed at high temperature from the layer that we used, and then once they get saturated, then the zinc and tin tend to deposit, and by having oxygen in the surroundings, so they get oxidized, and the gold cap remains as the oxide grow, and we saw gold cap also on the surface, on the top end of the nanowires. And we confirmed once again with XRD that this is a mixed oxide. We call it ZTO, zinc tin mixed oxide. We use this oxide for different sensing, and we find that out of these 4 gases that we have measured, methane, hydrogen, because these are all commercially important gases. So it is sensitive to ethanol, ethyl alcohol, selective to ethyl alcohol. Now, this sensitivity, is there any way to change that? For instance, we also know that a hydrogen sensor is getting very important. So what we did is we loaded those nanowires with palladium. It's a noble metal particle, nanoparticle, by a chemical reduction route. I will not mention them. And what we did is we deposited about 20 to 60 nanometer of particle all over the places of the nanowire. And we did the gas sensing measurement once again. And what we see here is quite interesting. So originally, if you remember, the mixed oxide was sensitive, more sensitive to ethanol and less sensitive to hydrogen. So it's just response is 4.4 against 21.6. But once we put palladium nanoparticle in the system, then the things gets reversed. It becomes more sensitive to hydrogen and less sensitive to ethanol. So what we see here, that we have some tools to change the sensitivity of a particular material system by doping them, for instance, with palladium or noble metal. Some people are using some other material as well. So I think with that, I will finish this. I will not go through the mechanism that we proposed. Summarize in the conclusion. So what we have discussed at the beginning is that gas sensors are very important devices used widely in the industry, and they're getting even more important nowadays in the era of IoT, where sensors are going to be used ubiquitously. They will be used even in our home for home environment monitoring, will be used in the health system, and so on and so forth. And then what we did is shared our experience with 2 material systems, and we have found out that we can grow this nice, well-structured, good enough morphology of mixed oxide in 1D form by simple thermal oxidation process. We need to control certain parameters, and the process doesn't involve highly sophisticated equipment or doesn't involve highly costly chemicals. And what we found out, that we have a thin layer on the top of the titanium core, and in spite of the fact that aluminum is insulator in bulk form, but we have this thin layer allowing electron tunneling, and hence allowing the sensing to be possible in this particular system. And we get a highly sensitive and selective sensor for certain gases. We also have seen that a zinc oxide, tin oxide system is very, very interesting in the carbothermal reduction process. It can allow us to create a lot of different morphologies by changing different parameters. And we have found out that zinc in mixed oxide are sensitive to certain gases, and we can even change their selectivity by doping them with different system, different nanostructure material. So with that, I have to thank you all very much, the audience, for being with us, and thank you.
Okay.
This is acknowledgement, the Ministry of Higher Education, which funded the initial project through high impact research and then FRGS, etc.
Okay, thank you very much, Prof. Haseeb, for the very interesting and very informative presentation. Now I would like to open the discussion, the webinar for Q&A from our audience. I think we can spend 5 to 10 minutes for Q&A. If you want to ask question, I would like to request for you to at least identify yourself, where are you from, either from IUM or from UM, from any other university, and please ask the question. If not, Prof, I have a question, one question for now. In the first system that you did, you apply the metal on top of the Ti64 commercial alloy, is it?
We started with Ti64 commercial alloy.
Is there any specific reason why you go for that type of alloy?
Yes. So we know from our initial experience is that making titanium nanowire on pure titanium is difficult because we cannot do it in dry air. We have to use a controlled atmosphere with a controlled amount of moisture, etc., etc. And in spite of that, the coverage of the nanowire, the morphology is not so good. So we wanted to try other titanium-based material. And other titanium-based material that we find easily available and expensive is this particular alloy. This titanium Ti64 is widely used in automotive industry.
Okay. Does the presence of vanadium affect the
and
material?
we also wanted to see the effect of other alloying elements. And what we find out now that the vanadium does not take part in any process. They remain inside the oxide and the particle. They do not come up to the surface because everything that happens here is on the surface. So if they do not segregate selectively to the surface, they do not take part in this nanostructure formation.
What's the percentage of vanadium in Ti64?
The vanadium was 4%.
4%.
And 6%.
Any question from the audience?
Assalamualaikum.
Waalaikumsalam.
I'm Amania from UTM.
Yes.
Ya, silakan Amania.
I have two questions here. First, for zinc oxide and tin oxide, for your mixing, you said just now you use the commercial powder, right, for zinc oxide and tin oxide. Is it the commercial powder is nanoparticle or nanowire?
No, let me answer this. Maybe I go one by one. So this is commercial, chemically, let's say chemical grade powder, so that we can buy. Obviously, we don't want to introduce any impurity, so we bought it from Sigma Aldrich. And these are particles that contains that has a size of let's say 60 to 80 micrometers. So these are just normal powder, 60, 80 micrometers.
Okay.
So,
okay.
not nano.
Yeah, clear. Okay, second question. Why you mixing zinc oxide and tin oxide using activated carbon powder for ball milling?
Because the process that we utilize here is called carbothermal process. So in this, it's a reduction process. What we want is, we want to convert the zinc oxide from microparticle to nanostructures. Now, in order to do that, we have to change the phase. So in order to change the phase, we now heat them. If we heat them without carbon, then we will not be able to vaporize them easily. So we use carbon because carbon will reduce our tin oxide and zinc oxide, and zinc having a very low vapor pressure. I'm sorry, I think it's very high vapor pressure. So they will easily vaporize. And then when they easily vaporize, together with tin, and they will go and deposit on our substrate. And on the substrate, when they redeposit, we hopefully expect that they will now form a nanostructure. So that is the whole idea. So without this, this carbon, we cannot produce this nanostructure. Let me show you. I think I have one slide, which I quickly skipped over. What happens when we do not mix carbon? I think, yeah. So this is, can you see?
Yeah, yes, I can see.
Okay, so if you look at number B, in number B, we did not use activated carbon in the mixture. And what we see is that there is no nanowire. We just see that initial gold layer becomes gold island, which is normal, I think, at high temperature. But the nanowires cannot grow because we do not have the supply of zinc from the boat yet. Because in order to get the supply of zinc, we have to reduce them and create zinc vapor, which will come over to our substrate. Is it clear?
Yeah, okay, thank you. Very interesting presentation.
Thank you very much.
Thank you so much.
Prof, there is one question from the chat. Hello, Prof. Very interesting and informative talk. I have a question.
Thank you so much.
At what temperature you do the sensing test? The question comes from Monica from UTP.
Okay, then that is a very interesting, important question, and my apology, I forgot to tell you this. And if you probably saw some of the figures, the sensing temperature is high because it has to be high in gas, in metal oxide semiconductor. So we did the sensing in the case of titanium oxide at 650, because that was the optimum that we get. We get a high signal. We could go values, but the response would be lower.
Okay. Any more questions from the audience? I think the presentation for me is very interesting.
Okay, thank you very much. So I also take this opportunity to all our listeners and viewers. So if you are interested in this area and you find any possibility of collaboration, so we are open to it. We have a big group here now. We are trying to gather. We have people from engineering, and Dr. Wong, Dr. Suryani is, I think, present with us, and Dr. Lai from NanoCat is also present with us. So we are working together. So we welcome any collaboration that you may tend to have.
Okay, thank you, Prof. Haseeb. I think with that I
Assalamualaikum, Prof. Haseeb.
Okay.
Waalaikumsalam.
Okay, I have a question. My name is Hussein from UTP.
Okay, thank you.
All right. First of all, thank you for your presentation. Very informative, Prof. Okay. My question is, I think you mentioned just now one of the important part of doing the sensor fabrication is the sensing material in terms of the thin film, right? Can you share a bit more in terms of how do you manage to create a consistent thin film for your sensor fabrication?
What we do here is probably I can go back. Let me show you. We create an ink, which means that we mix the sensing material with a mixture that contains alcohol and also that contains some surface active agent. So we create a paste, not a paste, a liquid that we can disperse. So the liquid will contain a vehicle and also our nanostructures, and then we drop them onto the surface. And if the viscosity is controlled, then we can get a uniform spread of the material over the surface. And if you see this, let me highlight this. And the way they are arranged on the surface of this electrode depends on how much liquid, how much solid you put into that carrier vehicle of the liquid. If it is too small in amount in the original liquid, then you don't have continuous connection of the layers. So layers do not, the particles do not bridge, so you don't get any signal. And what we need is enough particles that are more or less statistically randomly distributed, and they are connected at different places randomly, and they create, in effect, a continuous conduction path. So that is how we ensure. And we have done the test, and we have seen that in our case, between 2 to 5% loading, we could get a structure where we have some kind of conduction path at different places. And that is good enough to give us a consistent signal. And if we go beyond this, then we create a very thick layer, and they would short circuit the whole thing. The resistance is very low. They do not change in response to the gases, etc., etc. So this is something that appears to be good in our case. Did I answer your question?
Yes, Prof. So maybe I want to ask a bit more in terms of the thin film thickness.
Yeah.
What is the thickness of the thin film? And then I think you mentioned just now that you're using drop cast, right, to disperse the particular sensing material, correct?
Yeah.
Okay. Right. May I know what is the thickness of the sensing material?
The thickness is determined by the thickness of the particle. So if you look at the, let me show you this one. So basically, in ideal case, we would have this. So let me have the marker.
Right.
So we would have this. And the thickness that you see is the thickness of the particle, which is a few micrometers.
Okay.
And we want them to touch just on the surface at the outer nanowire contacts. Is that okay?
Okay, all right. Thank you, Prof. For the
Okay,
explanation.
thank you so much. Yeah.
I think we can have one more question, Prof. Is it possible?
Okay, no problem with me.
Okay, last question. I think the Prof is retired now. Any question? If there is no question, okay, I'll like to say thank you very much for our honorable speaker today, Professor Haseeb, for spending your time with us today, and also to our viewers who also spending your time to join our webinar. I would like to apologize for any shortcoming from my side. This is my first time trying to have, Google Meet and YouTube all together. So with that, I end the webinar. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Let me just say thank you to Dr. Zahirani. Even though you said that this is the first time, but you did very well. So congratulations. And I also would like to thank again Dr. Noor Asikin for organizing this.
Thank you
to all viewers.
Thank you also from me for accepting our invitation to be our speaker. Thank you so much.
Okay. Goodbye. Thank you.
Thank you. Assalamualaikum.
Waalaikumsalam.
Macam mana, okey? Lega. Aduh, nervous.